Graph as an ADT can be described as a data structure for storing adjacency relationship. The properties which are applicable on the graph as an ADT includes the number of vertices which are present in the graph, number of edges present, number of adjacent vertices present, and number of connected vertices. All these are included as a properties of a graph. Now, operations which are applicable on the graph as an ADT includes, as in other ADT, inserting and removing of an edge, inserting and removing a vertex which is present on the graph, and then traversing through the vertices and the edges present in the graph. Traversal algorithms are used to visit and process the vertices of a graph in a systematic way. The graph traversal algorithms that are applicable for both the directed and undirected graphs include the breadth first traversal, or which is also referred to as the breadth first search BFS, which make use of a recursive algorithm and a queue. And the second one, the depth first traversal or the depth first search, also known as the DFS, which make use of a recursive algorithm and a stack. The traversal of the graph or the order of the nodes visited in a graph by BFS and DFS is not unique. The traversal of the nodes depends upon the starting vertex selected and also the order of traversing the adjacent vertices of each node, which may be different in BFS and DFS. Both DFS and BFS make use of recursive algorithms to visit and process each and every vertex of the graph in a systematic way. Since the graph has no root compared to that of a tree, to start the traversal, we have to arbitrarily select a vertex and visit all its adjacent vertices in an alphabetical or ascending order. If the graphs are not connected, move back or backtrack to another vertex and start traversal again from that vertex until all the vertices in the graph are visited. Now we will try to understand the term meaning of adjacent vertices. For a directed graph, a vertex V is said to be an adjacent vertex of vertex U if there is a directed edge starting from U and ending in V. So in directed graphs, the direction of the edge matters, and also both the vertices should be sharing a common edge, or it should be the endpoints of a common edge. In case of undirected graph, if there is an edge between U and V, then it is said that both U and V are adjacent to each other, or they are adjacent vertices. Before moving into DFS, we will try to understand what is a tree and what is a spanning tree. A tree can be defined as a connected simple graph without cycles. So to understand what is a tree, we should first understand what is a simple graph. Simple graph is a graph without parallel edges and without any self-loop. And a connected simple graph is a graph in which all the vertices are reachable from both the end vertices. Or it is a subgraph in which there exists a path between all pairs of vertices. So a tree is a connected simple graph without any cycles. So with the definition of the cycle, we can understand that cycles are paths which can have only the end vertices repeated. So now a spanning tree of a graph is a subgraph, and we know what is a subgraph. Subgraph will be having the subset of nodes and subset of edges of a graph. So a spanning tree is a subgraph which is a tree and contains all the vertices of the graph. So a spanning tree can be defined as a subgraph which has only a subset of the vertices, and it is a tree. A tree, as we have already seen, is a graph which has no parallel edges, no self loops, and there is all the vertices are connected and without any cycles. Depth first search. DFS using a stack follows last visited node first explored strategy. The depth first search algorithm traverses a graph in a depthward motion. DFS explores all the edges from the discovered node which is on top of the stack, and then backtracks from the top node on reaching or on exploring all the adjacent nodes. The edges that lead to an unvisited node are called the discovery edges, while the edges that leads to a already visited node are known as back edges. The purpose of the DFS algorithm is to visit each vertex while avoiding any cycles. Steps to implement depth first traversal algorithm. Step 1. Define a stack with size equal to the number of vertices present in the graph. Step 2. Select any of the vertex as a starting point for traversal. Visit that selected vertex and push that vertex onto the stack. Step 3. Visit all the non-visited adjacent vertices of the current vertex on top of the stack. While visiting each of the adjacent vertex, push it onto the stack. Step 4. Continue visiting all the vertices until no new vertex is left non-visited as an adjacent vertex. Step 5. If all adjacent vertices of the current vertex on top of the stack are visited, then use backtracking and pop the vertex on top of the stack. Step 6. Repeat step 3, 4, 5 until the stack becomes empty. Step 7. When the stack becomes empty, that means we have visited all the vertices present in the graph. This will give the final spanning tree or the DFS tree by removing the unused edges for traversal from the graph. Now we will see an example for the depth first traversal on a directed graph. First step, define a stack of size equal to the number of vertices present in the graph. So here number of vertices present is 5, so we are defining a stack of size 5. Now select vertex 0 as the starting point for the traversal. Visit vertex 0 and push it onto the stack. Now find the adjacent vertices of the current vertex which is on top of the stack. The current vertex which is on top of the stack is 0. The adjacent vertex of 0 is 2, as there is a directed edge starting from 0 to 2. Visit the adjacent vertex 2 and then push it onto the top of the stack. Now see the adjacent vertices of the current vertex 2 which is on top of the stack. The current vertex 2 has an adjacent vertex 1 as an adjacent vertex. Visit vertex 1 and push it onto the top of the stack. Now see whether there are any adjacent vertices for the current vertex which is on top of the stack, which is 1. We can see that even though 0 is an adjacent vertex of 1, it is already visited. Then backtrack, as it is not having any other vertices, adjacent vertices which is not visited. Backtrack and then pop the current vertex which is on top of the stack. Now check whether the current vertex 2 which is on top of the stack is having any other unvisited adjacent vertices. As we can see that 2 is not having any unvisited adjacent vertices. Backtrack and pop the current vertex on top of the stack. Now we have reached vertex 0. Now see whether there are any unvisited adjacent vertices for the vertex 0. We can see that 3 is an adjacent vertex which is not visited. So visit 3 and push it on top of the stack. Now check whether the current vertex 3 which is on top of the stack is having any unvisited adjacent vertex. We can see that 4 is not visited and it is an adjacent vertex of 3. Visit the vertex 4 and push it on top of the stack. Now from 4 which is on top of the stack, see whether there is any adjacent vertex which is not visited. We can see that 4 is having 0 as the adjacent vertex but it is visited. So backtrack and pop the current vertex which is on top of the stack. Now check whether the current vertex 3 which is on top of the stack is having any unvisited adjacent vertex. We can see that 3 is not having any adjacent vertex. So backtrack and pop out the current vertex on top of the stack. So now we reached back to vertex 0. Check now whether 0 is having any unvisited adjacent vertices. We can see that 0 is not having any unvisited adjacent vertex. So pop up the last vertex 0 from the top of the stack. Now the stack becomes empty. The graph which is left out with the 2 unvisited edges can be considered as the final output of the DFS traversal, and it is also known as a DFS tree or the spanning tree. The DFS traversal of a graph, whether it is a directed or undirected, will produce a spanning tree or a depth first search tree as a final result. The spanning tree is a graph without cycle.